Today we are going to discuss characteristics of dry friction and problems involving dry friction. As with previous lectures, we have certain objectives, and that is to understand the characteristics of dry friction, draw a free body diagram including friction, and how we can actually solve problems involving friction. There are certain activities associated with these topics. A reading quiz. I'm going to discuss applications, characteristics of dry friction. We would take a look at some problems involving dry friction. There's a concept quiz. There's a group problem solving, and an attention quiz that would wrap our session. So, based on the readings of this chapter, let's take a look at the first reading quiz. A friction force always acts blank to the contact surface. And there are four options here: normal at 45 degrees, parallel at the angle of static friction. And the correct answer is C, parallel to the contact surface. So the correct sentence here would be: the friction force always acts parallel to the contact surface. The second reading quiz: if a block is stationary, then the friction force acting on it is blank. If a block is stationary, that means the mu sub Sn should be greater than or equal than the friction acting on it. So if a block is stationary, then the friction force acting on it is A is correct. What are some of the applications of friction, and where is it that we can identify friction in some of the engineering design? Well, a very simple system that most of us are familiar with is designing a brake system for a bike. The principles of friction that's involved here would actually make this system to work. So the questions that we need to answer here is how much force is needed here, how much force is needed to the pad itself, how can we design the pad, what should be the thickness of the pad, what should be the material for the pad, and how we can actually design such a system to be able to deliver that much friction force so we can apply to the rim of the bike itself and pretty much be able to design the system correctly. So in order to do that, we need to start by applying the principles of friction. We need to draw the free body diagram and to be able to identify how much force is needed to stop such a system. The other application here is a man here in this figure shown inside a garage trying to pull a refrigerator. It would be nice if he would know what would be the most appropriate angle in which he can pull this refrigerator. Should he pull it that way? Should he pull it downward? What is the appropriate angle that makes him to use the least amount of force to pull this refrigerator? So what are some of the characteristics of dry friction? Friction is defined as the force of resistance acting on a body which prevents or retards slipping of the body relative to a second body. I'm going to read this again to highlight some point. Friction is defined as a force of resistance, so friction is a form of force. It is resisting other forces or other force acting on a body. Friction force has a tendency to prevent or retard slipping of the body relative to a second body. Now, when we talk about the second body, and this could also mean a second surface. So make sure to keep that in mind when we talk about the second body. We're also referring to a surface. We can refer to a surface. So, or you can have more than body on top of one another or relative to one another. So how do we come up with the force of friction? Much research went into how we can actually study this. So after we determined what's the best way to study it, then we started designing the experiment and run the experiment. So experiments show that frictional force acts tangent to the contacting surface in a direction opposing the relative motion or tendency for motion. So if you look at it, if we blow up this surface that's shown down here under a microscope, we would see that there is no one surface that really, no matter how smooth it is, under a microscope, we would see this kind of an action, and we would analyze the situation and adding all these little friction forces up to come up with a one force, and that is summing all of those. And of course, it's going to be an average force because the force that would be developed at the corner of this block that I showed down here, both corners would be different than the force that would be generated at the mid surface of the block. But we take the average of that for our calculation purposes. So for the body shown in the figure to be in equilibrium, after we draw the free body diagram, obviously F must be equal to P. Again, this F is the average force that's shown here, but it's referred to it as one force F. And the force P is the force that it has a tendency to move this object, to pull it to the right of the page, but that would be resisted by a force F, which is a friction force. Remember that every time you're trying to pull or move such a block, there is also inertial forces as well. But those are applied in dynamic situations because inertial forces don't come into play unless we apply the force P very quickly. But for the sake of friction, P is usually applied slowly, and there will be no variation of P over time, although there are some, but again, for static calculations, we don't consider those. Now, in dynamic analysis of an object or a body or a structure, then we bring in the inertial forces, and those would also have a tendency to prevent the object from moving either way. But that's really the topic of another discussion. So what would be the magnitude of the normal force N to the surface? Looking at the free body diagram, taking summation of forces in the y direction. Y is up to the page, if this is the y direction. Then W must be equal to N. And then also W times X must be equal to P times H if you want to take the summation of moments about the point O that I just identified by a red mark down here. So let's take a closer look at some of other characteristics of dry friction. The figure on the top right hand side of the page shows the applied force P versus the resisting force F. So as the force is being applied, and again, this is the 45-degree angle of the P versus F diagram. We didn't intentionally set that to be 45 degrees, but this is just happened to be the curve itself after we generate that from the experiments. It is roughly going to look something like that. So we assume here that tipping does not occur, of course, otherwise we won't be able to study friction. If there are overturning moments or tipping is to occur, then we won't be able to study it in this case. So we are going to set up the experiment in such a way that there will be no tipping, and then we are gradually increasing the magnitude of the force P for the same reasons that I just described, because we do not want to produce any kind of inertial forces, since we only want to study friction. So we need to make sure that we follow these two rules before we can run the experiment. So this experiment shows the curve that you see here on the right hand side. So let's study this curve a little bit closer and see what we can achieve. So as we are increasing the load P in an almost 45 degree angle, F would increase. Now there's F sub K and F sub S, so don't worry about those for now. But let's say at some point we call that F sub K, and beyond that we keep increasing that until we reach F sub S. Okay, and after that the block start to move, so we're going to see motion. So up to a certain point we start from 0, we gradually increase this force P, and we don't see any motion of the block, so block is stationary with 0 movement or displacement until at some point beyond which we would see this block start to move. Now it's not going to jump right away since we are gradually applying force P, so gradually the magnitude of F, the friction, would reduce because we just overcome that, and as this block starts to move we reach a level of force F sub K, and we really can't go anywhere under F sub K. That's really our limit, and at F sub K we are increasing this P. So as we're increasing P from this point on, F sub K remains a constant, although the block is moving. So as we are increasing P, this is one value of P here, as we are going to the right, the block is moving. However, the friction force, or F sub K, we set that as our limit, would remain a constant. So that's what really experiment told us. There are also resultant normal and frictional forces. The frictional force is F, and the resultant normal is N, as I just showed you. So really the rest of this slide would show you what I just described. Now it's important to realize that the value of F sub S is correlated to the normal force N by a factor mu sub S, or by a coefficient mu sub S, when we call that a coefficient of static friction. So this is nothing but mu sub S, or mu S. Mu sub S is more common, and that is called the coefficient of static friction. And you can imagine that that also depends on the surface itself, right? The rougher or smoother the surface, that would affect the coefficient of static friction. And according to N, F sub S would go up and down, right? It would increase or decrease depending on the value of mu sub S and N. So these are the two. There's actually a little typo here. So that's really how it works. Let me fix this here as I'm going through this. Makes it easier. So the value of mu sub S depends on the two materials in contact, which translates to the surface, the roughness of the surface of both of these material. So after the block begins to move, as I just explained to you, the friction force drops as it is shown on this figure to mu sub k n, and that is called the coefficient of kinetic friction, and that is less than mu sub s because that is after the object gets into motion. So it is also important to realize that the friction force may be less than the maximum friction force. Again, as you see on this kind of this figure here. So because object is not moving, we cannot really assume that the friction force is at its maximum. So unless we state that motion is impending, then we really cannot make that assumption. So at the point in which the block just begins to move, there will be a maximum friction force that we saw on that diagram, and that is nothing but F sub s, which is mu sub s multiplied by n, and mu sub s is the coefficient of static friction. So if we take a look at the block that is shown here, just when it is at a point that's about to move or start to move, then we would combine n and F sub s, because now remember we have two forces. One is F sub s, the other one is n, and we find the resultant R sub s, and of course now we need to use the tangent of this angle, mu sub s, or phi sub s, which is F sub s divided by n, and as such the tangent of phi sub s would be mu sub s, using this simple equation down here. Okay, so how can we actually determine the coefficient of friction for different surfaces or different objects? So if we put a block as such, this blue block up here on an inclined surface, the way it is shown here, this is our object, and we gradually tilt this plane until the block just begins to slip. So we're increasing theta sub s, this is the angle, and gradually we start down here, we gradually incline this surface until we reach a point that the block just begins to slip, and that angle there, that would be the angle of inclination, or simply inclination, is denoted here as theta sub s. Then we would we would put the coordinate system as such. One would be in this direction, the other one would be of course perpendicular. So the direction of x here would be parallel to the surface, and the direction of y-axis would be perpendicular to the surface. It is supposed to be 90 degrees. So this would be our x and y axis. And we can really locate it anywhere. But we take the summation of forces into y, we set that to 0. As such, n minus w, the cosine of theta sub s, would be 0. And we take the summation of movement in the x direction, we set that to 0. As such, we're going to get this equation. Now we are going to use these two equations. We simply divide them by one another. Since they're zero, both of them could be. We can equate the two. Well, this was an accident. So what happens is we're going to calculate theta, a tangent of theta sub s as such. So this type of simple experiment is going to allow us to actually find the mu sub s between two materials in contact. So what are some of the steps? What are the steps involved in solving problems involving dry friction? These steps are shown here. Step number 1, as with other static problems, we would draw the necessary free body diagrams. Then we make sure that we show the friction force in the correct direction. It always opposes the motion or impending motion. We would determine the number of unknowns. Again, we cannot just make the simple assumption that F is mu sub s multiplied by n unless the impending motion condition is given. Then we would apply the E of E equation of equilibrium and appropriate frictional equations to solve for the unknowns. Okay, so let's take a look at some of the cases here before we can start an example. So let's try to take a closer look at impending, tipping versus slipping. And that's where the overturning moment comes into play. Remember that if somebody is trying to push this object the way it's shown, if they apply a force suddenly, and they may make this object to tip, right? So it may simply tip the object about this point and make it to fall. Now we don't want that to occur. So for a given W and H of the box, H is from here until from here to here, from the surface of friction to the point in which force P is applied. So this is H, that's shown down here. So we have a box of given W and H. How can we determine if the block will slide or tip first? That's a very good question to ask here. Now, in this case, we have 4 unknowns. Can you identify these 4 unknowns? Well, it is shown here on this free body diagram down here, or on this one down here. Those 4 unknowns are P, W, F, and N. Of course, there are a relationship between them. F is equal to P, and W is equal to N, using the summation of equations of equilibrium. And now we need to make other assumptions here to be able to calculate the unknowns. And what are some of those assumptions? Think about what are some of the assumptions that we can make here. So assume slipping occurs. In that case, F would be mu sub s n, or mu sub s multiplied by n. In that case, we can solve for x, p, and n. And we want to make sure that we're going to check to see the distance x, which is the distance of the normal force from the center of gravity of this object is between 0 and b over 2. So we want to make sure that x is somewhere between here to here. We're going to check for that. Or we can assume tipping occurs. In that case, we know that x must be b over 2, because the tipping would occur about this point, right? About the tipping point. And we would solve for P, N, and F, and we would check to make sure F is less than or equal to mu sub S N. Otherwise, there'll be no tipping. So we want to make sure we check for all that. Now, that brings me to the example that we can solve together here. So let's take a look at this example. A uniform ladder weighs 30 pounds as shown. The vertical wall is smooth, and that means there's no friction there, but there's a friction at the floor, and the floor is rough, and U sub S is 0.2. Now, this type of problem is very important for calculating when designing the ladders. You've probably seen those ladders, and there is they have legs, and at the bottom of the legs there's those padding and that is provided, and those paddings are designed actually according to similar principles, make sure that the ladder won't slip as the forces applied to it in different angle and from different directions. So the floor is rough, and U sub S is a 0.2. Our problem here is to find out whether this ladder remains in this position when it is released. So we're holding it in position now. We have the length of the ladder. It's actually 26 feet, so it's actually a tall ladder. One way to avoid any kind of a safety issue with these is reach the point B with some of these more like mechanical arms. But we don't, let's say we assume we don't have that kind of a luxury to reach a point B. So what we try to do is we try to see if this ladder remains in position, whether it is released. With the information that we have the weight of the ladder, and we have the length of the ladder, we have the distance it is away from the wall. We don't even have the angles, but we can calculate the angles if we need to. Any of these angles, we can calculate them. Of course, this angle is 90 degrees. So knowing one of these angles, we can easily calculate the other, knowing that this is the right triangle. So A, B are the points of contact. A is the point of contact with the floor. B is the point of contact with the wall. And remember, there is no friction here between at point B between the ladder and the wall. So the plan is to draw a free body diagram, and then we determine the unknowns. We show them on the free body diagram, and then we make any friction assumptions that I just went over. Then we apply equations of equilibrium and any kind of a friction equation if appropriate, and we are going to solve for the unknowns, and then we check the assumptions to make sure that we did the problem correctly. So if we draw the free body diagram of the ladder, this is drawn in AutoCAD, so the free body diagram of the ladder is shown as such. The force that's shown in blue is the W, the weight of the ladder. It is a 5, 12, 13 type of a triangle. That's a ratio that's also shown here. It's a 5, 12, 13 type of a triangle. The reactions at point A is shown as F sub A and N sub A. N sub A is the normal surface acting at point A. The normal surface acting at point B is shown as N sub B up here. The distance is also shown. The weight of the ladder is applied at the center of gravity, and very important, and that is halfway up through the ladder. So it's a point 12 feet and 12 feet, and of course it's halfway through, so it's right here, somewhere here, in which the distance from the wall is 5 feet, and the distance from the floor for that particular location is 12 feet. So that's really the location of the centroid of the ladder. Now there are three unknowns here, n sub a, f sub a, and n sub b. So all we need to know is the dimensions, and we know w, the weight of the ladder. So we need to calculate n sub a, which is the normal to the normal at point A, normal force, f sub a, which is the force parallel, that's the friction force, f sub a, and n sub b, which is normal at the point B. So simply we use the equations of equilibrium. We take summation of forces in the I, we set that summation of forces in the y direction, we set that to 0. N sub a minus 30 would be 0. As such, n sub a would be 30 pounds. So that is n sub a. Then we take the summation of moment about point A. We set that to 0 to be able to calculate n sub b. So 30 times 5 is minus n sub b times 24. And that this is the weight of the ladder, and 5 is the moment arm for the blue force that's applied at the centroid of the ladder. So as such, n sub b would be 6.25 pounds, and we take the summation of forces in the x to 0 after calculating n sub b. Now we can do that to calculate f sub a, and f sub a turned out to be 6.25 pounds. So we're going to now check the friction forces to see if the ladder slides or stays. F sub max would be mu sub s multiplied by n sub a. So as such, the mu sub s, the coefficient of friction, is given here as 0.2. Multiply that by 30. It turned out to be 6 pounds. Now, since f sub a that we just calculated up here, this is f sub a. Since this is greater than the maximum force caused by the friction that I just calculated, 6 pounds, then the pole will not remain stationary. After we let it go, it will move. Now think about the power of the tool that you just have. You can calculate with the knowledge that you have. You can calculate something that only engineers or people that are familiar with engineering, and they can calculate. Right away, you would know after this calculation that if you let go of this ladder, the ladder would move. Now, I won't recommend you guys test this at home, but at a much maybe smaller scale, you can test this out with a piece of wood. A small piece of wood could be used here in this case. You can lean it against the wall and try to test it out. Now, want to make sure it's shorter so it will be no harm done in case it falls down and in case it starts to move. So these are the type of things that you can pretty much set up to just test out for yourself. Do your calculations, then test with a piece of wood to see if everything would work out the way your theory would tell you. So fundamentals of engineering provides you with very powerful tools for the analysis of different situations and scenarios. That was just a good example of that. So let's take a look at a concept quiz after we went through what we did already. So concept quiz number 1, a 100-pound box with a wide base is pulled by a force P and mu sub s of 0.4. Which force orientation requires the least force to begin sliding? So the question that I raised at the beginning of this lecture under applications now could be answered here for this particular situation. Now we are given 4 choices here: A, B, C, and D. Now should piece of A be the answer, piece of B, or piece of C. This is drawn in AutoCAD. That's why it is shown as such: A, piece of B, and piece of C in parentheses. So if we have a 100-pound box with a wide base, it is pulled by a force P, and friction is 0.4. Which force orientation requires the least force to begin with? And the correct answer is actually A, P sub A, because of if we use any other force in the actions in the directions that they're given, and they require, those forces would be larger than P sub A. So this would be the least force to for this box to if we apply this box start to slide. So then the second concept quiz: the ladder is positioned as shown. Indicate the direction of the friction force on the ladder at point B. Okay, it's another interesting question here. Now, if you position the ladder as such, in what direction, what would be the direction of the friction force on the ladder at point B? And we are looking for the direction of the friction force at this point. Should it be perpendicular? Should it be actually perpendicular to the surface here, like that? Is it parallel to the surface, like that? Or could it be any other angle, like that? Okay. And based on what we have discussed so far, if there's a tendency for this ladder to move at point B, and the friction is going to act in the opposite direction. So if the ladder slides to move, start to slide to the left, toward the left of point A, and B would start sliding downward. Point B is going to move downward in this direction, and the friction force would act at a direction opposing the movement, the direction of the movement of B. So it's going to be acting in this direction. It's going to act parallel to the surface AB, the way it is shown. So the correct answer is C, that shows the parallel force. Let's do a group problem solving. We have a refrigerator that's shown as such. It weighs 180 pounds. The coefficient of friction is given, mu sub s as 0.25. We would like to determine the smallest magnitude of force P that will cause impending motion, tipping or sliding of the refrigerator. So again, similar to what we have discussed, but the problem is now given here. So the plan is we're going to draw a free body diagram of the refrigerator. We will determine the unknowns. We make any friction assumptions if we need to. Then we will apply the equations of equilibrium. And of course, the friction equation is appropriate to solve for the unknown. And we will check the assumptions as required. Very similar to what we did in the previous problem. So we're going to draw the free body diagram. The 180 pounds is going to be applied at the center of gravity of the refrigerator. Force P is shown with the dimensions given, which is applied 4 feet from the ground. The center of gravity for this object, since it is actually given here, we haven't gone that far yet to talk about how to calculate the center of gravity, but for an object like that, it is shown here, 3 feet and 1.5 feet from the right or to the right of point A. So this is the free body diagram. The friction force is shown here as F. The normal force is also shown, assuming that X is the distance in which N is applied at, and that X is a distance away from point O. So there are 4 unknowns here, P, N, F, and X. We assume that the refrigerator slips first, then the friction equation F would be mu sub S n, and that's going to be 0.25 n. Okay. So then we take the summation of forces in the x, set that to 0, and p minus 0.25 n. That would be the equation, the resulting equation. And still we have two unknowns, n and p. We are going to move on to the next equation. We take the summation of forces in the y. We set that to 0. As a result, n minus 180 would be 0. As such, we can calculate n as 180 pounds. And knowing n, we're going to plug it back to this equation. As such, 180 by 0.25 would be magnitude of P, which is 45 pounds. Now we take the summation of moment about O and we set that to 0. As such, the value of the x would be calculated. X would be 1. It is less than 1.5, so we are okay. If it was more than 1.5, then it wouldn't work because it is going to fall. N would be somewhere here. It must stay within this range from here to here. Okay. So if P is 45, the refrigerator slips. And assume 45 for a P of 45 pounds, the refrigerator slips. Now, let's take a look at an attention quiz, and we wrap our session. A 10-pound block is in equilibrium, as shown. What is the magnitude of the friction force between this block and the surface? Assuming mu sub S is 0.3, the correct answer is shown here. C, 2 pounds. It's a 10-pound block in equilibrium. So that is 10 pounds. Okay, this is the best I can do in showing the pound here with the mouse. So we simply do the calculations, and you can easily calculate what would be the magnitude of the friction force between the block and the surface. So try that, and you should have C as 2 pounds. Now another ladder problem. If the ladder is positioned as shown, what is the direction of the friction force acting on the ladder at B? This is very interesting to take a look at again. If there is any slippage to occur, and then B is going to pretty much slide downward. As such, the magnitude of the opposing friction force would be upward at point B, so the correct answer is D. That pretty much brings me to the end of this lecture. Let learning continue, and thank you for your attention.